We've learned about how the ultraviolet catastrophe was the first problem to be solved by a new kind of quantum theory. This was the idea that by proposing that certain kinds of energy must be quantized, that is, exist as certain discrete values rather than any possible value from a continuous set of values, mathematical models could accurately correlate with observation. The next issue that begged explanation was called the photoelectric effect. This was a strange observation whereby electrons could be ejected from a piece of metal when irradiated with light, but only when that light was above a certain threshold frequency. This seemed odd because it would seem that the light would simply have to be above a certain energy, and the energy of a wave of light is dependent on its amplitude or intensity. But it wasn't the case. Below a certain frequency of light, no matter how intense the beam was, it wouldn't eject an electron. But above that threshold frequency, even the faintest beam of light could do it. The person who solved this problem was the famous Albert Einstein, by using principles developed by Planck when he worked with blackbody radiation. As Planck said, the vibrational energies of the atoms must be quantized. So Einstein said, so must be the light. In order for this to make sense, he described light not as waves, but as a stream of particles, which we call photons, whose energy depend on their frequency according to this equation, which utilizes Planck's constant, which can also be rearranged to give the energy dependent on the wavelength. This explained the photoelectric effect, because an electron would be ejected when struck by a singular photon of sufficient energy, which is why the beam of light does not need to have any particular intensity. Whereas if the photons in the beam of light are all below a certain frequency, it won't matter how intense the beam is, because none of the individual photons will have enough energy to eject the electron. This meant that the intensity of the light did not correspond to the amplitude of the wave, but rather to the number of photons striking the surface, which explained another observation that the number of electrons ejected increased with increasing brightness. Brighter light, more photons, higher likelihood that photons will collide with electrons. Although this explained the photoelectric effect, the idea of the photon was very confusing because some aspects of light are best explained with the wave model. But clearly, some aspects were now better explained with a particle model. The only explanation is that light is simultaneously both particles and waves. This bizarre phenomenon, still not fully understood and impossible to truly illustrate with any image, is called wave-particle duality.